Okay, so first of all, I'm Dominik, and I will be talking today with you about what I did in the spring semester. I wrote a semester paper, and my goal was to figure out more about this famous millennium problem. Exactly. But first of all, I want to thank Alessandra and Anna for organizing the sock map and taking the time to organize everything and look that everything goes the right way. Then maybe a disclaimer up front. As you can imagine, in solving these equations, very rigorous maths are involved. And today, in this frame that we have with people from very different backgrounds in maths, and also some physicians should be among us. So I cannot go too far and too detailed in what I will do. So just be aware that most things will be explained in the level of intuition and not very detailed. Just as a disclaimer up front. What else? I wanted to ask, who is here in their bachelor's? Maybe raise your hand. And I assume the rest are masters. So about 50-50. Yes. So, okay. And before I start, just want to say, if you have any questions, feel free to interrupt me anytime. Yes, you just shout, Dominik, I don't understand the thing you're telling me, so I will try to do my best to explain to you what's going on. Okay, so let me start with this scenario. I prepared a drawing. So in this drawing we are in Zurich. We are at the Limmat. This is the river that's down in the city, for the ones that do not know. And this is Jessie. And Jessie has a ball in her hand. And for 1 second, assume maybe that the ball has about the same density as water, the water that's flowing in the river. And then Jessie throws this ball into the river. And she asks a very natural question, or a question that maybe one can ask himself. So Jessie asks, where will be my ball in 5 seconds, say? So will it be over there or down here? Where will it be? And a mathematician formalizes this problem and says, okay, more general, can I get a definitive answer for any positive time? So is there a way of predicting where will be the ball for any time? And sadly, to date, we do not know yet. And yes, so, and this is this famous known problem of the Navier-Stokes equations. This flow of the water in the river can be modeled, as your physician fellows may tell you, by the Navier-Stokes equations. And these are still not fully understood. And we do not know if we have a definitive answer to this or not. So maybe let's formalize everything a bit and introduce some notation. So the setting of the problem. We're given this flow, and how can we describe this flow? So our flow will be a three-dimensional vector, which shall depend on the space. So where are we located within the river? And also at what time are we looking at this flow? And this is just the velocity of the water. So the velocity of the fluid at the point x, and x is an element in 3 space dimensions and at time t greater or equal to 0 will just be denoted by u of x comma t. And this shall be a vector. So a vector valued function, or sometimes also called a time-dependent vector field. Then we denote the pressure of the fluid at the point x and at time t greater or equal to 0 by p of x comma t. And then some further notation. We denote the initial velocity vector field by A. So if Jessie is standing by the river and is looking into the river, she can at time t equals 0 see what the water is doing. Obviously, this is not very practical, but suppose that it is the case that she knows what is the velocity doing at time 0. And this velocity at time 0 will just be noted by A of x. So this shall be equal to u of x at time 0. Okay, so far so good. We have now introduced some notation. And now we can write down what the equations are that model this problem. So, and maybe I should say, here I picked x to be in 3 space dimensional Euclidean space because obviously the river is a bounded domain. It's like not infinitely long. And yes, but in order to model this, I chose this framework in R3. It really doesn't matter. One can also consider a bounded domain, and things will be very similar. But there are some complications with bounded domains, so I chose the entire space. Okay, so here are these equations. So these are the so-called Navier-Stokes equations, and this velocity field should satisfy these 3 conditions in order to model this flow of this river. So the first equation, we take the velocity field u and take the first derivative with respect to time, then add u dot nabla applied to u. And that's just a shorthand notation for this right here. So we take ui and then multiply it with partial I of the vector we're applying it to. So we're taking here like the dot product of u with nabla and then applying it to v. And then this shall be equal to minus the gradient of p plus Laplace u. Exactly. And this is just a variant of a direct application of Newton's laws. So this first equation can be derived by using the law that the sum of all forces equals the mass times its acceleration of a point. And yes, so I hope this is somewhat digestible. I wrote down here also these operators. This we have already talked about. This one right here is the gradient, as I think most of you should remember. And this is the Laplacian, which is just taking the second derivative in the ith direction and then summing all of these directions up. And then we have the divergence of a vector field is just taking the ith derivative in the ith direction of the vector field and then summing it up. And then the second equation is called the equation of continuity, and it just states that the vector field shall be divergence-free. And it is derived by the law of conservation of mass from physics. And then the last condition is just this initial condition, which just says that at time 0, our time-dependent vector field should equal A. Okay, and then I label these equations NS1, NS2, and IC just so we can then use them later. So any questions so far? Yes, sure. Yes, that's a very good question, and a question I really do not want to go too deep into. So it should definitely have sufficient enough decay at infinity, A. And to provide this framework we are going to work with today, usually one assumes A to be, I don't know, anyone has ever heard of Sobolev spaces? Okay, a few. So A should be in H1, in the Sobolev space H1, usually is a natural assumption. Yes. Any other questions? Okay, so now we have these equations, and now what do we do? How can we solve them? So, any suggestions? Well, obviously it won't be easy because it's a millennium problem, and they pay you quite a bit of money if you solve them. So it's not quite straightforward how to proceed from here. But let me first introduce some spaces, or recall the definition of some spaces you should have seen somewhere in MMP, so mathematical methods or physics, or analysis 2. So we keep at the top these equations, and then we introduce these two spaces. So the first space is just the set of all smooth, compactly supported functions on R3, which is just the set of all phi from R3 into R, such that phi is C infinity, and the support of phi is compact in R3. For the ones that do not remember what the support of a function is, it's just the closure of the set where the function doesn't vanish. And as we're taking the closure, as I just told you, this is obviously closed, and in order to be compact, by Heine-Borel we know that a set is compact in Euclidean space if and only if it is closed and bounded, so we only require the support of phi to be bounded. And then we have that it is also compact. So this is this first space, and the second space is the space of smooth, compactly supported, divergence-free, time-dependent vector fields on R3 times 0 infinity, which is just the set of all functions, psi from R3 times the time interval 0 infinity into R3, such that psi is C infinity. So, and then we want also the support of psi to be compact. And additionally, we want psi to be divergence-free. And obviously, in order for the divergence-free to make any sense, we need that it takes values in R3. So, yes. And with these spaces, we can now maybe think back with these equations, what can we start with them? And the difficulty about these equations and about general PDE, partial differential equations, is that they are understood pointwise. So we want these equations to hold on any point in space and time. And this is quite hard to understand for us. But maybe we can understand them in a distributional sense. And that's what I want to explain to you, how these equations can be understood as distributions, or as distributional equations, I should say. Yes?
Yeah, just one thing. Why do you time interval is open at 0, right? How do you deal with the initial conditions?
This space, okay, it's a good question. The thing is here, where we want the support of psi to be within our time domain. So if the support of psi is compact in R3 times the interval 0 infinity, then psi will be 0 before psi arrives at 0. So in a region of 0, so if this is 0, then in a region of 0, psi will be anyway 0. So it really doesn't matter. We just want the support of psi to be somewhere here. So it shall not touch 0, the support, and it shall not explode to infinity. So we can use distributional theory. Okay, so maybe we can work with the second equation and see what we can do. Okay, so any other questions maybe? So let me just call this the weak derivation. So we have these classical equations, and we want to find a weaker version of them by distribution theory. So we assume that U is smooth on R3 times the interval 0, infinity. So we assume we have a classical solution to this problem. Satisfies ns1 and ns2. Okay, so we assume we have a classical solution, U. And then we let phi be smooth, compactly supported on R3. So we take it out of this set. And now we want to test this function, ns2. So we multiply ns2 with phi and integrate. And let's see what we get. So I think I have enough space. So we take the second equation, this is divergence of U, and then I just told you we want to multiply with phi and then integrate in space. So we do so. And we have that this is obviously equal to 0 since the divergence of U is 0 by ns2. And now we just write down this definition, what this means. So the divergence is the sum for I equals 1 to 3, integral over R3, partial I ui times phi dx. And now we do what everybody does in PDE theory, and it is called Lewis-Nirenberg's recipe. We integrate by parts. So, and how can we do this here? So we just write down, okay, we want to move this partial I over to phi. And this is just nothing else but the following. So if we let partial I on the vector field U times phi, then it will once hit here I forgot the I. It will once hit UI and once it will hit phi. So we have to subtract that. And we end up with this. And now we can just read what this is. This is nothing else, but here we have this term, partial I, of ui phi. And that's nothing else but, again, the divergence of u times phi dx. And why is that? Because this is a vector-valued function, and we multiply it with this scalar. So this is the divergence of that. And then here, we're multiplying ui with partial I phi. So this is nothing else but the dot product of u with navla phi. And now we can use analysis too. And since this function here, phi, has compact support, so on some ball, we can choose a ball such that within this Euclidean ball, the support of phi is within that. So then the support of u times phi will also be within that ball. And then we can invoke the divergence theorem and integrate over the boundary of that ball. But as the support of this will be contained in that ball, it will be 0. So we can, this will integrate to 0 by the divergence theorem. And this is what we are left with. So let me write down what we just figured out. We find that 0 equals the integral over R3 of u dot phi, gradient phi dx. Questions so far? Okay, and that was done doing integration by parts using the second equation. We derived that this distributional equation, and we can do something similar with the first equation, but that will take much more time. So let me just tell you what we will get. So similar. Okay, similar as above, we can show, and again with integration by parts, and since here we're dealing with time-dependent vector fields in the second space, we will integrate also in time, and this will end up being the following. So similar as above, one can also integrate by parts that equation when we multiply it with some psi. And it's just a little bit more work, but one can derive that this holds for such a smooth solution. Obviously, in order to make these calculations rigorous, we also have to assume some integrability on u. But I really do not want to talk about that. Just assume that, for example, u has compact support, and then everything is fine. Maybe compact support in space. Okay, questions so far? Sorry. So we have successfully transformed this equation ns2 into this. And this holds for any phi. And ns1 can, in a similar way, be transformed into this by multiplying with psi and integrating by parts. Okay, and this is maybe a motivation to give this as a definition. So we want to find a weaker version of these equations, so we define it like this. So a function u from R3 times the interval 0 infinity into R3 is a weak solution of this problem if it satisfies this first equation, which corresponds to the one I wrote down there, and this equation here, which is what we derived down here. And I see there is a typo here. The time should not be integrated. So we're here only integrating in space. But it is not. Yes, and here also this should be only of space. So take this away, and this. And that's what we wrote right here. So also just look at this. And then we still want to somehow link the initial condition to such a vector field which satisfies these two distributional equations. And we just do it in a very natural way in the L2 norm. So the u of x comma t minus a in the L2 norm should go to 0 as t goes to 0, which just means that u of x comma t goes towards a in L2, which is what I wrote right down there. So that's how we link these two. And obviously some further Sobolev regularity is required, and also Bochner spaces are involved, which, has anyone heard of? No, these are usually used when studying time-dependent partial differential equations. And an energy inequality should also be satisfied in this definition, but due to time restrictions, I'm not able to develop this part of the definition. But I just wanted to explain to you how from the, assuming that we have a classical solution, we can derive at this weak version. And, okay, but any questions so far, maybe? Yes?
Why are they called weak?
Okay, that's a very good question. So we have these equations up there which are understood pointwise, right? And if we assume that we have a solution to those, then they will satisfy this weak version. So this is kind of like a weaker condition than the one above. And this can be shown very straightforward, as we did here. And maybe we can start something with this. So this wouldn't be all that useful if we wouldn't have the following theorem. On the reasonable assumptions on the initial vector field A, which is this one, there exist weak solutions. And this is something we know, and we can prove. But then still the question in the room remains, are these weak solutions also classical solutions? And that's our hope. And that's the reason why we go down to a weaker version, which we can understand very well with functional analysis, and then try to go back to our original equations. Then, I'm not sure how's time, but maybe we can. Any other questions? I wanted to explain you how we can find these weak solutions. So one of the biggest challenges in this equation right here, or in the equation on the top, ns1, which is this one, is this term right here, dealing with this term. Because this is the nonlinear part of the equation. And also in the distributional sense, it is still nonlinear. And there is a technique how one can deal with this using mollification by convolution, which I would like to explain to you. So this will be for the ones maybe that have taken the course on MMP. They will maybe remember what a convolution is and a mollifier. So we want to show this term, and we want to deal with this nonlinearity. And I want to explain to you how one can do this. So let's do a sketchy proof. So we let eta be a mollifier from R3 times 0 infinity into R. And we let eta be C infinity. To be a mollifier, we want it to be greater than or equal to 0. And we want the support of eta to be, usually one assumes in a mollifier the support to be in a ball, but here we will do a trick with the time domain. And we will assume it to be in the unit ball in space times the time interval 1, 2. And we will assume, obviously, that this mollifier sum up to 1. So we want to use this approximation. And then fix some m in n. And now we want to construct an approximation of our equation. So m shall be the index of the approximation, and we define eta m of x comma t to be m to the 4 eta of mx mt, as one does with mollifiers. Okay, and the convolution, also we define it as usual, so the convolution of eta m with a time-dependent vector field at the point x comma t shall be the integral from 0 to infinity, integral over R3 of eta m x minus y t minus s dy ds. And then here obviously this v of y is missing. So v of y comma s dy ds. This is just a convolution of these two functions. And okay, this is a very standard setting, but we have chosen this support to be a bit different. So to not be in a unit or in a ball, but away from 0 in time. And this will give us the following very nice property. We note that, so if we have, this is time, so, and we can cut this into these pieces, 1 over m, 2 over m, 3 over m, 4 over m, 5 over m, and so on. And we note that if we are on one of these pieces, so if we choose some t to be in one of these pieces, which is just in this time interval k divided by m, k plus 1 divided by m, and we want to know how this convolution works. So this convolution is interesting when this is non-zero. Otherwise, it's not interesting, because then we can just integrate over the part where it's non-zero. So we look at a t in this section of the timeline that is non-zero. So eta m of x minus y, t minus s should be non-zero. Then what can we conclude? We just go back to the definition of eta m, and this was just this, but this is non-zero, so this must be 0 if we are assuming that it is. This is non-zero. I'm messing things up. Yeah, so in order for this to be non-zero, we require this to be non-zero, right? And this is non-zero exactly in its support. So in this set, so in time, this just means that that 1 is strictly less than our argument here, which is m times t minus s, and this is less than 2. So the input of this, which is this, should be less than 2 and greater than 1 in order to be non-zero. And then we can just do some algebra. We can divide by m, and then we have 1 over m is strictly less than t minus s, strictly less than 2 over m. And then we can move the s over here, and we get that this is strictly less than t minus 2 over m. And we can move the s over here, and the 1 over m over here, and get that this is strictly less than t minus 1 over m. And now we can go back and see the t's that we're considering. We're considering in this section right here, which is just a section of the timeline. And t will be, in this section, bounded by k plus 1 over m. And if we subtract 1 over m, this just gives k over m. And in this direction, it will be bounded by k over m minus 2 over m, so k minus 2 divided by m. Okay, and what have we learned? So, hence to define eta m convolution v on such a piece of the timeline, k divided by m, k plus 1 divided by m, we only use the definition of v on k minus 2 divided by m, k divided by m. Why is that? Because only in this interval, eta m will be non-zero. So only there we will use v, the definition of v. If we are considering t's, which are in this time interval. So it's like, here is maybe um, and we say we have constructed, okay, maybe I shall move on. So we look for a weak solution of the following. 0 is less or equal than the interval from 0 to infinity. Integral over R3 of dot partial t psi plus Laplacian psi plus, and then here, instead of using this weak definition, this one right here, we use, instead of using here this u to make it linear, we plug in here the convolution of eta m with and then the rest we leave the same. So for any psi which is smooth compactly supported divergence free, and we want this to hold. We find such a where here we deal with this by convolution. And the nice thing is, if we are constructing and say we have constructed up to here, then this part here, in order to define in this section, this part will be given, because we are only using from here to the left. So then, if we have this given, this will just be a linear equation in which will be much easier to solve. And that's how one deals with this nonlinearity in the approximation. There are several other ways of approximating this term. but I chose to do it by convolution because it's somewhat natural. Okay, so I'm running out of time, but one can then show that UM converges to a sum U. And that's nice because then this will converge towards U, and this will converge towards U, and we will have this weak version. So we can pass to the limit. And this convergence is obviously very complex. It's, again, in some Bochner-Sobolev space. And I shall also say here, obviously, at some point, for the ones of you that took functional analysis, Banach-Alaoglu will be involved, where we will have this sequence bounded. Okay, questions so far? Maybe this was a little bit too far, but I think the people who have seen this maybe were able to follow what the idea is. So the main idea is just to take this support in this way, such that we can construct this in these time sections. So no, that's a good question. So the question is, if we change the domain, if we change the setting from R3, natural settings are the torus, which has no boundary, and another natural setting is a bounded domain. Also, manifolds can be considered. I have never looked into manifolds, but usually bounded domains and the torus will work exactly the same. And you encounter the exact same difficulties. And in fact, the bounded domain is is a little bit easier than the entire space. And yes, that's what I can say. Other questions? So, okay. Now I've talked a lot, and maybe you haven't understood a lot, but one question still remains in the room, and that's are weak solutions, as we defined them, classical solutions? And are they unique? So this, as I told you at the beginning, is still unknown. But some partial results have been established. And that was also a part of my semester paper, to look at these partial results. So a weak solution cannot be shown yet to be a classical solution. But if we assume some slightly more regularity on classical solutions, they can be shown to be, on weak solutions, they can be shown to be regular. And this is something that Sarin, so give me just 2 or 3 minutes more, I'm sorry. Sarin, 1961, found this condition, which is known as Sarin's condition, that if a weak solution, U, satisfies, in addition to being a weak solution, this integral, so this integral is finite for exponents Q and S, which satisfy the conditions over there, then U is indeed a classical solution. So if you can construct a weak solution which satisfies, which has finite integral in this sense, then you will be done to any given initial condition, A. And then several other results have been established. There is a list of regularity results of this type that you can look at, but I focused on these two because these are the ones that interested me the most. And this is another condition. So if we have a weak solution, and we assume in addition that the gradient of the third component of the velocity can be integrated in this way, with exponents satisfying that condition, then it is indeed a classical solution. And we can also show that it is unique. So, questions so far? I think there are some, but to be honest, I didn't look into them because obviously this involves function space theory, which is what I focused mainly during my studies. But I'm pretty sure this is the most successful way of looking at it, as it is general in PDE theory. And then I just want to say maybe one last thing, that this problem that we started with, it may look very fundamental, and it may look as if we're asking a question that is very easy and easy to understand, but we do not know if solutions exist. And this seems to be like a very important problem, as I told you today. But I would just want to tell you the opposite, that this is not really that important in practice. So people outside of this room and outside of doing mathematical research really do not care about the answer to this question. Because today, engineers and physicists will just use an approximation to this problem, which will be much better than just knowing that there is a solution to this problem. And besides that, if we can solve this problem, we can just say that there will be some solution to these equations. But we cannot write it down in formulas, and we cannot learn a lot about its pointwise behavior. So it will not be all that useful for real-life applications. And that's what I wanted to tell you, Tim. As is everything we do in pure math. Okay, any other questions? Then I think there is an apéro, right?
Do you clap first?
Yeah, you can clap.